All right, we're going to finish chapter 6 and review for the test. All right, so we were at the heat of vaporization for methanol at 25 degrees Celsius in 1 atmosphere. All right, so on the test, you're going to be given your standard enthalpies of formations. You're either going to be given a chart with all of them or given the ones you need for the problem that you're looking at. All right, so vaporization, you have to know that that is a CH3OH. Vaporization means you have a liquid going to a gas. CH3OH gas. All right, so when you're looking at your standard enthalpies of formation, you got to find your delta H naught formation for both the liquid and the gas. And you're going to take the product, the gas, and subtract the reactant, the liquid. When you get the delta H for this, you have to heat a liquid to make it a gas. And so your answer better be positive because all of your vaporizations have a positive delta H. All right, so you go to Appendix C, you look up your values. All right, and so you see that on Appendix C, the delta H naught formation for liquid methanol, the liquid right here, is negative 238.7 kilojoules per mole. And the gaseous methanol from that table is negative 200.7 kilojoules per mole. All right, and so to get the answer, you take your products, the negative 200.7 kilojoules per mole, but we have just 1 mole. All right, so that's negative 207 kilojoules products minus the reactants, negative 238.7 kilojoules. All right, so that's kilojoules per mole, but we have 1 mole. So the 1 is understood. You don't put in 1 when there is just one of the molecules. It is understood that that is one of those going to one of those in your balanced reaction. All right, and so that is your delta H naught for this reaction. And so when you do that, you see that you're going to get a positive 38.0 kilojoules. Push that on your calculator. Positive 38.0 kilojoules. All right, so it is an endothermic and it feels cold. And how do we know that it feels cold? Anytime something is evaporating, if you put acetone, put something that evaporates fast, you can really feel the cooling. But that's how sweat works. You sweat, the water evaporates, and that cools the body. All right, and what's going on? Well, your liquid is going to a gas, and that is a cooling endothermic process. All right, so we're going to find delta H for this reaction. So again, you're going to have a chart. You're going to look up your delta H naught formations. So here is the reaction. All right, so either within the problem, they'll give you the delta H naught formations you need, or you look them up in the appendix or table 6.2. All right, so your aqueous methanol. All right, so methanol will come liquid, methanol will come gas, methanol will come aqueous, and they're 3 different numbers. So be sure to be aware of the given state. All right, so this one is negative 245.9 kilojoules per mole. Oxygen is not listed because all elements in their natural state have a delta H naught formation of 0. The formaldehyde is negative 150.2 kilojoules per mole. And water liquid, again, make sure you're getting the liquid, not the gas. We have a negative 285.8 kilojoules per mole. So now when we find our delta H for this reaction, you're going to take your products, all right? And so your products, you have a negative 150.2 kilojoules per mole. All right, but this time you see that it's not a 1. You have 2 moles of that, so you have to multiply it by 2. Plus, you have your negative 285.8 kilojoules per mole, but again, we don't have just 1 mole of that. We have 2, so times 2. So that is your products. Then you're going to subtract your reactants, and that is a negative 245.9 kilojoules per mole. And then you have 2 moles of that times 2. And I'm going to end it there. You could add 1 times 0 if you want. Anything times 0 is 0. All right, so the 0 ones I don't put in. All right, so you get your products, add those all up. Then you get your reactants. You take your products minus reactants to get your delta H for this reaction. All right, so when you push the buttons, all right, so again, I would get a number for my products. I would get a number for my reactants. I would do this in steps. I would not just put it on the calculator and say equals. All right, and so you would have your delta H naught for this reaction to be negative 380.2 kilojoules. So this is an exothermic reaction. And so this releases heat. So this would get very hot. Right, so you will be given the table or you will be given the numbers on the various problem. Again, if that is wrong. All right, so that should say gas. This is an element in its natural state. All right, so that is 0. So those may not be given. You have to know that elements in their natural state have a delta H naught formation of 0. All right. Let's do, so we have, all right, so let's write the reaction for the delta H naught formation for CH3OH. All right, so you have to know what that means. So the definition of a delta H naught formation, that is the formation of 1 mole from elements. So it's the formation of 1 mole from elements in their natural state. All right, so that means that we would need to have carbon, because carbon is an element in our compound that was asked for. We would have to have hydrogen, but in the natural state, we know that hydrogen is a diatomic gas. And we would have to have oxygen. And again, we know oxygen is a diatomic gas. And that's going to produce 1 mole of CH3OH. And you have to have a balanced reaction. All right, so you have 1 carbon. Yes, you have 4 hydrogens here, so we have to have 4 hydrogens here. We have 1 oxygen here, and so again, anytime you're writing a delta H naught formation reaction, many of these require a fraction. Of course, you don't have to put the 1 in front of the carbon, and you don't have to put the 1 in front of the CH3OH, but you do have to know that the definition is you're going to form 1 mole from elements. That is the delta H naught formation. Many times you will need to use fractions in order to do that. All right, so that is the end of chapter 6. All right, so now we're going to work some problems. And the first one we're going to work is a lab problem. All right, so I'm going to figure out why that's a blue screen. Still a blue screen. All right, that worked. All right, so we have lab data. All right, we have a temperature, and that is 19.5 degrees Celsius. So this is experiment 4. We have the pressure of the lab on the board, 29.82 inches of mercury for this day. All right, and then we have our mass of test tube plus our MnO2 plus our KClO3. And that number is 2.2583 grams. All right, then we got our mass of beaker. The mass of the beaker on the triple beam balance, 152.58. All right, and so then we did the experiment, and then we got, after we finished our experiment, let it cool, we got the mass of the beaker with the water on our triple beam balance, and that weighed 563.99 grams. And then the mass of the test tube after heating. And that had a mass of 1.7003 grams. All right, and so now it says calculate R. So in order to calculate R, so we have PV is equal to nRT. Solve for R, that's PV over NT. Divide both sides by NT, and you then have R by itself. All right, so the pressure and then the R value, that is the correct answer. So the theoretical answer, 0.08206 liter atmospheres per mole Kelvin. All right, so that tells us that the pressure has to be in atmospheres, our volume has to be in liters, N is always moles, and T is always Kelvin. All right, so T is very simple. We add 273.15 to our temperature in Celsius, and we get a 292.65. All right, so we add 2 decimals, subtract or add 1 decimal, we get 1 decimal for our answer. And so we have our temperature. It is 292.7 Kelvin. All right, pressure. This is where we have to know what we did in the lab. In order to get the pressure, we're going to take our 29.92 oh, that's not it. Well, we could use that as a conversion. 29.82. Sorry, that's given. I know 29.92 is 1 atmosphere, but we're going to do it the usual way. All right, so that's inches of mercury. There are, in 1 inch has 2.54 centimeters, and 1 centimeter has 10 millimeters. And so when you push all the buttons there, you get a 57.4. That would be a 757. 757.4. So a 757.4. So it's a little less than 1 atmosphere. This is in millimeters now of mercury. All right, so when we did the lab, we had our flask. All right, but in our flask is water. So there is water in the flask. H2O is in there. Oxygen is here, but also water evaporates. So you have water liquid, but you also have water vapor. And so this gas is not just oxygen. There is some water vapor there. So you have to look up on the chart and get the pressure of water at 19.5 degrees Celsius. So in your lab, you're going to have to find your temperature from your data sheet. You wrote down your temperature. All right, and then you're looking up on a chart to see the pressure of water at that temperature. And when you do that, you find it is 17.5. At 19.5 degrees, your pressure of water is 17.5 millimeters of mercury. And that comes from a table in the book. So you can find your pressure of water at any given temperature on this chart. All right, so our pressure of the lab, so the pressure total, Dalton's law of partial pressures, the pressure of the lab is equal to the pressure of the oxygen plus the pressure of the water. And so when we're doing PV is equal to nRT, we want the pressure of water, volume of water, moles of water. We want oxygen, pressure of oxygen, moles of oxygen, volume of oxygen, temperature of oxygen. So we don't want the pressure of the lab, we don't want the pressure of water, we just want the pressure of oxygen. So you plug in your numbers, 757.4 millimeters of mercury is equal to your pressure of oxygen plus the 17.5 millimeters of mercury. And so we subtract 17.5 millimeters of mercury. We subtract 17.5 millimeters of mercury on both sides. And we get a 739.9 for our pressure of oxygen, a 739.9 millimeters of mercury. All right, now our answer was in atmospheres. We have to get our pressure of oxygen in atmospheres. So we have to take this and divide by 760 millimeters of mercury in 1 ATM. So now we have it in the correct units, and it is just the pressure of oxygen. We don't want the pressure of the lab, we want the pressure of oxygen, 0.9736 ATM. All right, so now we have our pressure and we have our temperature. All right, so let's, what are we going to do next? Let's do our volume of oxygen. All right, so the volume of oxygen. So the volume of oxygen is equal to the volume of water. So if we made 400 mils of oxygen, it's going to push out 400 mils of water. All right, so if we can find the volume of water that is equal to the volume of oxygen that was put in, volume of oxygen that goes in kicks out that volume of water. All right, so the density of water, we need this to 4 sig figs. So you can look this up in a table, you can Google it, whatever your temperature is. Density is temperature dependent. So at 19.5 degrees Celsius, the density is 0.9979 grams per milliliter. So you can use this for your lab, this number, or you can look up the actual density to 4 sig figs for your temperature. But it's going to be very close to this. It is not going to be a perfect 1. 1 is good for 3 sig figs. It is not good for 4. All right, so to get our density, that is, of course, the mass over the volume. We have the density. It's right here. We look it up. It's a constant for water at a given temperature. All we need to know is the mass of water, and that's where we use our beaker. So remember, we had the beaker with water, and that was 563.99. And then we had the beaker that was empty, and that was 152.58. All right, and so when you take your beaker and water and subtract your beaker, now you have your mass of water. And so the mass of water, after we subtract out the mass of the beaker, is 411.41 grams. All right, so now that we have our density and our mass, we can solve for the volume. All right, and so then the volume of water is your mass, 411.41 grams, divided by the density, 0.9979 grams per milliliter. All right, but again, our 0.08206 is liter atmosphere, so we don't want milliliters, we want liters. All right, so we got to get rid of milliliters, and so that is 10 to the minus 3 liters. And so the volume of water in liters is a 0.4123 liters. But remember that the volume of water is equal to the volume of oxygen. The volume of oxygen that came in kicked out that volume of water. And so there is our volume of water, which is the same as our volume of oxygen. So 412.3 milliliters of water got kicked out because 412.3 milliliters of oxygen went in. All right, now finally we need the moles of oxygen. And that is when we take our mass laws. So our reaction is KClO3 solid, MnO2 solid, produces KCl solid plus O2 gas. All right, and so when you have 2 and a 2 and a 3, you have a balanced chemical reaction. All right, and so after we heat it, it lost mass. The mass that was lost is your mass of oxygen. All right, so first we have to find the mass of oxygen, and then we will divide by the molar mass of oxygen to get our moles. So to get the mass, that is simply the mass difference between our test tube. All right, so when we added the KClO3 and the MnO2, the mass of that was 2.2583. Then we heated it, produced oxygen, displaced water, let it cool, and then we weighed it again, and it weighed 1.7003 grams. All right, and so our mass of oxygen is simply to subtract those 0.5580. All right, so your calculator is only going to say 0.558, but you have 4 decimals minus 4 decimals. You have to give 4 decimals. All right, and now this is the molar mass of oxygen gas. Oxygen gas is O2. That is a 32 for the molar mass. And so to get your moles of oxygen, you take the mass, 0.5580 grams, and divide by the molar mass, 32.00 grams per mole of oxygen. And so your moles of oxygen are a 0.01744 moles. All right, so now you have all of the data that you need to find R. Again, R is your PV over NT. So you plug in your numbers. The pressure that we found for oxygen was the 0.9736 atm. The volume that we just found for the water, which is the volume of the oxygen that went in to kick out that volume of water, is a 0.4123 liters. Moles right there, 0.01744 moles. And then the first thing we did was we converted our temperature into Kelvin, and that was a 292.7. All right, and then when you push the buttons, you get a 0.07866 liter atmosphere per mole Kelvin. And again, the error is here, so if you get a different number, it may just be because I didn't take intermediate answers and I kept everything in my calculator. All right, but if it's different in a different number, then there's something wrong. All right, so then it says give the percent error. All right, and so that is your experimental minus the theoretical over the theoretical times 100 is the equation for finding your percent error. All right, so we got in the experiment 0.07866. Theoretically, we should have gotten 0.08206. Divide that by 0.08206, and then you multiply by 100. All right, so here you have to figure out the sig figs of this. And so when you subtract these two numbers, you're going to have 5 decimals minus 5 decimals. You're going to give your answer to 5 decimals. And when you do that, in this case, I can see that that is going to be 3 sig figs. All right, so you'll have to push the buttons on your calculator, give your answer to 5 decimals. That's going to be 3 sig figs. It's going to look like 2 when you do this because that happens to be a 6. That happens to be a 6. That last decimal is going to be a 0. So you have 5 decimals, which is going to be 3 sig figs. Divide that by 4 sig figs times 100. And you're going to give your answer to 3 sig figs, a negative 4.14% error. When percent error comes out to be negative, you need to put it because that means that your answer is too low. So that does mean something. That means your answer is lower than expected. If you have a positive percent error, that means your number is higher than expected. So whatever you get, it's not an absolute value there. It is a percent error. The negative means it's too low. The positive would mean it is too high. All right, so that's how you would do a problem, do experiment 4. All right, let's do a Hess's Law problem. So a Hess's Law problem is they're going to give you a bunch of reactions and ask you for the delta H of a different reaction. All right, so here is the problem. So the question is, I want CH4 plus NH3 yielding HCN plus 3H2. And the question is, what is the delta H of this? All right, and so for a Hess's Law, you will not be given the delta H naught formations because you could just do products minus reactants, but those numbers are not given. Instead, they're going to give you some reactions. And so here is the 3 reactions to use. N2 plus 3H2 plus, yields 2 NH3. And they give you the delta H for this reaction. And it is negative 91.8 kilojoules. Then they give carbon plus 2H2 yields CH4. They give the delta H of that reaction. It is negative 74.9. And then they give you a third reaction. H2 plus 2 carbon plus N2 yields 2 HCN. And the delta H value for that reaction, 270.3 kilojoules. All right, so when you do a Hess's law problem, you have your reactant in the question. So your reactant in the question. Here we have to have CH4. So in the 3 data points that we have, 3 reactions, we have to have CH4 as a reactant. There's only one spot where you have CH4, and it is in the product side. In order to get that to the reactant side, we have to reverse the reaction. So remember, when you reverse a reaction, you have to change the sign of the delta H. So you're going to reverse reaction 2 and change this to a positive 74.9. NH3 is next. NH3 only shows up in one spot, and that spot is right here. Again, it's on the wrong side. And so we have to reverse the reaction. And so this is going to become a positive 91.8 when we reverse that reaction. We want 1 NH3 in our answer. The given problem has 2 NH3. So we're going to have to multiply that through by 1/2. So when we multiply this through by 1/2, we're going to have to multiply the delta H also by the 1/2. HCN. HCN is on the right. It's only in one spot. It is on the right side. We do not have to reverse this reaction. However, we only want 1 in our question. And so again, we're going to have to divide this by 2 or multiply through by 1/2, same thing. And we will change our delta H by dividing it by 2 or multiplying by 1/2. All right, so we're going to switch the first one. So we have CH4 goes to C plus 2H2. And the delta H of that is a positive 74.9 kilojoules. So I took, to get my CH4 on the left, I had to reverse the second reaction. When you reverse a reaction, you change the sign of your delta H. My NH3, I need to reverse that, but I also need to multiply it by 1/2 all the way through. So I will have my NH3 going to 1/2 N2 plus 3/2 H2. So I divided it through by 2 or multiply it through by 1/2. That's the same thing. So my delta H there is I have to change the sign to positive and I have to multiply it by 1/2. And that is a 45.9 kilojoules. So I changed the sign to positive, and then I had to divide it by 2. And now the HCN is on the right side, except I only want 1, so I have to multiply that through by 1/2. And so I have 1/2 H2 plus carbon plus 1/2 N2 yields HCN. And that has the delta H of half of this, which is 135.15. So I don't change the sign because the HCN was on the correct side. I wanted it to stay on that side. All right, but in the question, I only had 1 HCN, and so I had to multiply it through by 1/2. All right. So I would not have done the hydrogens because the hydrogen's in all 3 reactions. You do the NH3, it's only in 1. You do the CH4, it's only in 1. You do the HCN, it's only in 1 of the given reactions. All right, so when you add them up, you have to subtract. So this is an addition here. So this is an addition subtraction. So you can look at these as an equal sign. All right, so we're going to subtract 1 carbon from both sides. We are going to subtract 1/2 of a nitrogen from both sides. We are going to subtract 1/2 of a hydrogen from both sides. And this 3/2 hydrogen is now 1 hydrogen or 2/2 hydrogen. And so when you add them up, you have your CH4 plus your NH3. That's all you have left on the left side. On the right side, you've got HCN. Plus, you have 2 hydrogens here and 1 more hydrogen there, 3 hydrogens. And so when you add reactions, you add the delta H values. and this comes out to be 255.95. But since you added these, you have 1 decimal plus 1 decimal plus 2 decimals, and so you give your answer to 1 decimal. So 256.0 kilojoules is the answer to the delta H for that reaction. Another one like that. All right, so here is another problem using Hess's law. You have 2 carbon plus 2 waters yields CH4 and CO2. All right, so I want the delta H for this reaction. Back up here, we got a positive delta H. So a lot of times after you get your answer, they'll ask if it's endothermic or exothermic. So that is an endothermic reaction. Anytime you have a positive delta H, it is endothermic. And if they say, if you are holding the flask, how does it feel? Every endothermic reaction is cold or cool, depending on how endothermic it is. But cold is what I'm looking for. All right, so here's the data. I have carbon plus water yielding CO plus hydrogen. And the delta H for that is given. It is 131.3. All right, another reaction is given, and that is CO plus H2O yielding CO2 and H2. Delta H for that is given. Negative 41.2. And then the third reaction is given. CO plus 3H2 yields CH4 plus H2O. And the delta H for the last reaction given is negative 206.1 kilojoules. All right, so same thing. We go here and we are looking for carbon. All right, and so carbon only shows up in one of the given reactions. The only place that you will find carbon is in the first reaction. All right, but the carbon that's in the first reaction only has 1 mole of carbon. We need to have 2 moles of carbon. And so we have to take this entire reaction, including the delta H, and multiply it by 2. Water is in all 3 reactions, so you would not do that one next. Go to the CH4. CH4 is only in one reaction. It is right here. It is 1. It is on the right. You leave it the way it is. CO2 comes next. CO2 is in only one reaction, and it is this one. And it is going to stay on that side. So you multiply this one through by 2. You got 2, you got 2, you got 2, you got 2. And you have a 262.6 when you multiply it through by 2. And when you add that up, it's 262.6 minus 41.2 minus 206.1. And that's going to give you, I don't have, oh yeah, I do. 15.3 kilojoules. And so the delta H for that is 15.3 kilojoules, and it is endothermic. All right, we will review more for the test on Monday.